Now let's start covering CMOS logic design. Now we have already touched on this whenever we covered the inverter, and we looked at the NMOS inverter and we looked at the CMOS inverter. So if you can't remember that, I suggest you go back and have a quick look at both of those inverters. Now in the NMOS logic, the NMOS was a pull down logic, and we've got the diagram here. So in this NMOS logic here, we're actually pulling the output low down through this network here, and we have this depletion load device as the pull up network. But in CMOS logic, we've got both pull down networks and we've also got pull up networks. The pull down network is given by the NMOS device, and the pull up network is given by the PMOS device. And we've seen in this instance here, if we talk through these NMOS inverters, whenever the input goes high, this device here is turned on. When the device is turned on, there's a direct connection from here to ground, so this is pulled low. And whenever the input goes low, this device is off, and this device is always on. So if this device is off and this is always on, then there's a connection from here up to the power supply rail. So it means that this point here goes high. So that's how our inverter works for the NMOS. Now we've seen in the previous videos as well, when we looked at the CMOS inverter, if this input were to go high, it means that this device here will be on, but this device here will be off. So if this device is on, it means there's a connection from here to ground, so this is pulled low. So a high will give you a low. If this device is off, it means that the input is low, it means that this device is off and this device is on. So if this device is on, then there's a path from here up to the power rail. So it means that this point here is pulled high. So whenever we get a low input, we get a high output. So this is how both of these devices work. So we could summarize this using these 4 lines here. We could say that in a pull down network, so this is the pull down network, which is the NMOS network here, the output will be high if there is no path exists through this pull down network. So if we don't have any path down through here, then this point here won't be connected and it will sit high. Alternatively, for the pull down network, if the output will be low if there is a path exists through the pull down network. So if there is a path existing down through this network, it means that this point here will be pulled low. So that's how our NMOS device works. Now if we were to look at the path here, which is the pull up network for this CMOS device, we could say that we're going to have a pull up whenever the output will be high. So that output there will be high if a path exists through the pull up network. So if there's a path existing up through this way, then this point here will be pulled high. Now alternatively, again with the pull up, the output will be low if there's no path exists through this pull up network. So if there's no path existing up through here, this point here will remain low. And that's how each of these pull up and pull down networks work. Now if we want to make other gates other than inverters for CMOS, then we're going to have to use the pull up logic and the pull down logic together. So let's go ahead and we'll look at the NAND gate and the NOR gate, and we'll look at them in detail, and we'll see how the CMOS networks are actually going to be working and how we're going to design them. So let's take our time and we'll look at the CMOS NAND gate. Now we'll do this by comparing it to the NMOS NAND gate. So here's the NAND gate here, an A and B input and the X output, and this is the truth table for it. So the truth table for a NAND gate tells us that we get an output low only if both inputs are high. Otherwise, we get a high output. And we've seen that we designed this here as a pull-down network, which was the NMOS network. And what we did whenever we did this design, if you remember back, we looked to say, when does the output go low? Whenever the inputs are high. Now, the output is going to go low in this instance whenever both inputs are high. So what we're saying is we want to know, how do we get a path from the output to the ground? And we get a path from the output to the ground in this instance whenever A and B are high. So in this instance, when we looked at the NMOS gate, we were looking at a pull-down network, and we were looking at the values of the inputs that gave a low output. And we've written that down here. For a pull-down network, we're looking at it in terms of the high inputs that are going to give a low output. So this is a high input, it's giving a low output. And we've seen here that both of them have to be high. So whenever both of them are high, it means we're going to have to put both of them in series. So there's going to have to be, when this one goes high, this turns on. When this one goes high, this one turns on. There's a path from here to ground, and that means at this point is pulled low. Otherwise, if any one of these is off, there's no path flowing through, and that will give us these other three options that we have here. Both of them are off, there's no path, or any one of them is off and there's no path. So we've seen that whenever we did the NMOS design, and the most important part about this is this little line here. It really tells us that in order to work out this NMOS design, we need to look at it in terms of the high inputs, which give us the low outputs. Now, whenever we're doing the CMOS design, we're going to have to look at the pull-down network, and we're also going to have to look at a pull-up network. Now, in the pull-up network, we look at the opposite. We look at it in terms of the low inputs, which give us high outputs. So let's take our time and we'll work through the two possibilities, one for the CMOS pull-down, one for the CMOS pull-up, and then we'll add both of them together and we'll get our final CMOS NAND gate, which is this structure here. So if we look at it in terms of the pull-up network, we can look at it and we say, in terms of the low inputs, when are the outputs high? So here's the low outputs here. So we've got a 0, 0 there, we've got a 0 here, and we've got a 0 here. So we're looking at these inputs here, and we're saying, when do the outputs go high? So they go high in each of these. So it means that if A is low or B is low, it means that we're going to get a high output. So remember, whenever we're ORing things together, what we're doing is we're putting them in parallel. So we're going to have a pull-up network, which is the two PMOS devices in parallel. And we can see here that we'll have our A input, our B input, and we would have our output, which we call X. So this here is going to give us these three here. So we're saying that if A is off in B, if A is low and B is low, so this is low and this is low, these are PMOS devices, so that means that both of these are on. So if both of them are off, both of them are on, we've got this point here, we're pulled high. Or if any one of them is on, this point here is pulled high. So that's going to give us these three lines of the truth table. So now if we look at the pull-down network, so this is the pull-down network here. So I've actually done this one first and we'll look at this one next. So this is a pull-down network here. Now in the pull-down network, it says in terms of the high inputs, when are the outputs low? So these are the high inputs here, and this is the low output here. So we can see that the output is going to be low whenever both inputs are high. So in effect, what we've got here is the two of these values in series. So we can see here we've got the A and B in series. So we're going to have a low output here whenever this one goes high and this one goes high. So when both of these are high, these turn on and pull this point low. So this part of the CMOS pull down logic is going to give us this line here. So it means finally, in order to get the full truth table, we take the pull up network, that's a pull up network here, which is just this one, and we take the pull down network, which is this one here, and we put them together. And we can see here then, this is the final CMOS NAND gate, and this is the final output here, which is the NAND of the two inputs A and B. So let's take our time again and we'll just follow through this truth table for this little block here. We can see that if both inputs are low, so if these inputs here are low, then these two devices are off. So it means that there's no path from here to ground if both of these devices are off. And then whenever we look through these devices here, if both of these are low, it means both of them are on. So it means there is a path that comes up here to the high value. So it means we're going to get a value of 1. Now, I'll leave it to you to talk through the A and B 0, 1 and 1, 0. So work through those for yourself. So finally, we can work through the 1, 1. So if both of these inputs are high, then we're going to get a path from here to ground. So it's going to pull this point low. Also, whenever both inputs are high, it means that both of these transistors are off. So it means there's no way that this point can be connected to both this point here and this point at the same time. It's not possible because both of these are off. It means we're going to have the low output. So that's how our CMOS NAND gate works. And you can see that in the CMOS NAND gate, we have to take care of both the pull up path and the pull down path. So let's go ahead and we'll look at the NOR gate. And after that, we'll have a little think about why it is that if you notice when two of these are in series, the other two have to be in parallel. And we'll have a little talk about that as well. Now let's work through the CMOS NOR gate. Now this is the NOR gate symbol here, and this is the truth table. And we've already seen the NMOS NOR gate, and this is it drawn out here. Now we know again that the NMOS is a pull down logic. So in terms of the pull down logic, we say in terms of a high input, when are the outputs low? So in terms of the high inputs, when are the outputs low? We can see here we've got a high input here, here and here, and we've got the low outputs. So we can see that whenever any one of the inputs is high or both inputs is high, inputs are high, then the output is low. So we can see that we've got an OR function here, or equivalently, that both of the transistors are going to have to be in parallel. And we've got this here, we've got our A and our B in parallel, and we've got our depletion load device up here. So it means that if both of these are low, then both of these devices are off. If both the devices are off, then this point here is going to be pulled high, and we'll get a high output, and that's what we've got here. But alternatively, if any one of these inputs is high, or both of them is high, then we're going to have a path down through either here, or equally both at the same time, which will pull this low, and this will give us our NMOS NOR function. So that's a bit of revision, we've seen that previously. Now we know that in order to build this in CMOS, we're going to have a pull up network and a pull down network. So we'll just talk through the pull down first and then the pull up. So in terms of the pull down, we've seen here in the top line, it says in terms of the high inputs, we're interested when the outputs are low. Well, this is just the same as we did a second ago whenever we looked at the NMOS logic, and we can see that we've got the exact same setup. So there's nothing new there. Now for the CMOS pull up. In terms of the pull up, it says in terms of low inputs, when are the outputs high? So in terms of the low inputs, when are the outputs high? So this is this line here. So only when both inputs are low do we get a high output. So that means that this point here is going to be ANDed with that, this point. So in effect what we're saying is it's going to be A dot B, and it means that both of these are going to have to be in series. So we've got both of them in series, and remember in the pull-up network the logic gates are PMOS logic gates. So we've got this set up here, and you can check this again. If both of these are off, if both of these are low, then it means that the PMOS devices are on. So if they're on, then there's a path up here to the power rail. So this point here is going to go high, and that's what we've got here. Now we know that in order to build up the entire truth table, we're going to have the pull down logic here, which is going to give us the bottom 3 lines, and the pull up logic, which is going to give us the top line. And what we can do is we can place both together. We'll have our pull up logic here, and we'll have our pull down logic. And this is going to give us our output, which is A plus B naught, which is our NOR function. So take your time and make sure you understand how the CMOS, NOR and NAND gates are working. So now we've got an idea of how to build the CMOS logic, let's go ahead and we'll look at the half adder and the full adder built using CMOS in the next video. So thank you for listening. I'll get you in the next video. Goodbye.